There's a building in Poughkeepsie, New York that looks like any other data center from the outside. Inside, however, there are machines that operate at temperatures colder than the vacuum of deep space, processing information in ways that the classical computers around them cannot even begin to replicate. This is IBM's quantum data center, and it represents something that the technology industry has been debating, dismissing, and quietly preparing for the better part of a decade. Quantum computing is no longer a research lab curiosity. It is moving into data centers. It is moving into enterprise infrastructure. It is attracting hundreds of billions of dollars in investment from governments and corporations simultaneously. And it is about to change what a data center is, what it can do, and what it will cost to run one in ways that most people working in the industry have not fully reckoned with yet. So if you run a business, work in technology, or simply want to understand the infrastructure that is going to power the next generation of artificial intelligence, cryptography, pharmaceutical discovery, and financial computing, you need to understand what is happening inside these buildings right now. To understand why quantum computing matters so much for data centers specifically, you need to start with what is fundamentally wrong with the data centers we have today. Not wrong in the sense that they do not work, they work extraordinarily well, but wrong in the sense that they are approaching the physical limits of what classical computing can accomplish for certain categories of problems. The entire global data center industry runs on classical bits. Every server, every storage array, every network switch, every processor, and every rack in every building, all of it manipulates information as a sequence of zeros and ones. A bit is either on or off, a 0 or a 1. There is no in between. This model has been extraordinarily powerful, and Moore's law, the observation that transistor density doubles roughly every 2 years, has driven decades of exponential improvement in what classical chips can do. But Moore's law is slowing. Transistors are now so small that they are approaching the scale of individual atoms, and the physics of making them smaller further is becoming almost impossibly difficult. And there is a deeper problem. Certain types of problems are fundamentally hard for classical computers, not because classical computers are slow, but because the structure of those problems requires exploring an exponentially large space of possible solutions. And classical computers can only do that one step at a time. Drug molecule simulation, financial, portfolio optimization, supply chain routing at global scale, breaking or building advanced cryptographic systems. For these problems, even the most powerful classical supercomputers in the world run into walls that no amount of additional silicon can overcome. This is precisely the gap that quantum computing is designed to fill. And if you want to keep getting content that explains these infrastructure shifts in plain language before they become mainstream headlines, now is the time to like and subscribe. A quantum computer does not use bits, it uses qubits. Quantum bits that exploit the properties of quantum mechanics to exist in multiple states at the same time. This property is called superposition, and it means that a qubit is not simply 0 or a 1. It can be both simultaneously, in a combination that only resolves into a definite state when it is measured. A second property called entanglement allows qubits to become linked, so that the state of one qubit is instantly correlated with the state of another, regardless of distance. A third property called interference allows quantum algorithms to amplify paths leading toward correct answers and cancel out paths leading to wrong ones. Together, these three properties give quantum computers the ability to explore a vast landscape of possible solutions simultaneously rather than sequentially. For problems where the number of possible solutions grows exponentially with the size of the input, this is not just an incremental improvement over classical computing. It is a categorically different kind of computation. Google's quantum system solved a specific mathematical problem in seconds that was estimated to take the world's most powerful classical supercomputer 47 years to complete. That number is almost meaningless to comprehend. 47 years of continuous classical computation versus a few seconds of quantum processing for the same problem. That is the kind of gap we are talking about. Now, here is where data centers enter the story, and the entry point is more complicated than a simple technology upgrade. Bringing quantum computing into a data center is not like adding a new generation of GPU servers. It requires rethinking the physical infrastructure of the facility from the ground up. The reason is temperature. The superconducting qubit architecture used by IBM, Google, and many other leading quantum hardware companies requires operating conditions near absolute zero, specifically around 15 millikelvin, which is roughly 15 thousandths of a degree above absolute zero. To put that in context, absolute zero is minus 273 degrees Celsius. Outer space, by comparison, sits at around minus 270 degrees Celsius. A quantum data center running superconducting qubits must maintain temperatures colder than the void of the universe. This is accomplished using specialized equipment called dilution. refrigerators, which use a mixture of helium isotopes and a closed-loop cooling system to achieve and sustain these temperatures. IBM's Blue Force Kide cryogenic platform, co-developed with the cryogenics company Blue Force, stands just under 3 meters tall and 2.5 meters wide, and the floor beneath it must be capable of supporting roughly 7,000 kilograms of weight. This is not a server you slide into a rack. This is a piece of scientific infrastructure more closely related to a particle physics laboratory than to conventional data center equipment. The constant sound inside a quantum data center is not the familiar roar of cooling fans. It is the rhythmic pumping of compressors, forcing supercooled liquids through a system that is keeping the qubits isolated from the thermal noise of the room around them. Beyond temperature, quantum computers require vibration isolation, because even minor mechanical disturbances can disrupt the quantum states of qubits and introduce errors. They require electromagnetic shielding to protect qubits from interference from radio waves, Wi-Fi signals, and even the electrical noise generated by classical computers and adjacent racks. And they require specialized control electronics that translate classical signals from software into precise microwave pulses that manipulate the quantum state of individual qubits. All of this means that a data center operator who wants to host quantum computing systems cannot simply clear a floor and order some new equipment. They need to redesign their power delivery, their cooling infrastructure, their structural engineering, and their electromagnetic environment. The Open Compute Project, the industry standards body whose recommendations shape how the world's largest data centers are built, began working in 2025 to develop what it calls a quantum-ready certification, a framework for what a data center needs to do to credibly host quantum hardware at scale. That certification did not exist before because the need did not exist before. The fact that it is being developed now tells you everything about where the industry believes quantum computing is headed. The question of which quantum hardware architecture will ultimately dominate the data center landscape is one of the most important open questions in technology right now, and the answer is genuinely uncertain. Superconducting qubits, the technology used by IBM, Google, and OQC, require cryogenic cooling but offer relatively fast gate speeds. Trapped ion qubits, used by IonQ and Quantinuum, operate at room temperature. Microsoft has been developing a completely different approach using something called topological qubits, based on a new class of materials it calls topoconductors, which it claims will be inherently more stable and less error-prone than other qubit types. In February 2025, Microsoft unveiled a chip called Majorana 1, the world's first quantum processor built on topological qubits, calling it a transformative leap toward practical quantum computing. Microsoft's current quantum design fits inside a standard server rack and draws approximately 30 kilowatts, with most of that power going to the refrigeration system, keeping the qubits cold. For data center operators accustomed to racks drawing anywhere from 10 to 100 kilowatts for AI training hardware, this power profile is manageable, and the rack-compatible form factor is extremely significant because it means quantum hardware could eventually sit alongside classical compute in existing facilities, rather than requiring purpose-built separate facilities. The energy question around quantum computing is one of the most interesting and counterintuitive aspects of this story. Current AI data centers are consuming electricity at a rate that is straining power grids across multiple continents. Training a single large AI model can consume as much electricity as dozens of households use in a year. The build-out of AI compute infrastructure is projected to require gigawatts of new power generation over the coming decade. Quantum computing, by contrast, is not primarily a power consumption story. A quantum processor itself runs on an incredibly small amount of electrical power. The energy cost of a quantum data center is dominated by the refrigeration systems keeping the qubits cold, and even that is relatively modest compared to what classical AI training clusters consume. More importantly, if quantum computers can solve in seconds what classical systems would need thousands of hours to compute, the total energy consumed per unit of useful computation goes down dramatically. An analyst at UBS made this point clearly when she noted that if you are replacing a problem that would take thousands of hours of classical computation with a quantum computer that solves it in seconds, you obviously need far less energy for the same outcome. This means that at scale, quantum computing could actually reduce the energy intensity of advanced computation, even accounting for the power required to run the cryogenic cooling systems. That is a radically different narrative than the one surrounding AI infrastructure today, and it is part of why data center operators and real estate investment trusts are paying serious attention to quantum as the next major demand layer for their facilities. The cryptography story is where quantum computing intersects most urgently with the existing data center ecosystem, and it is the aspect of this technology that is causing the most immediate action even before large-scale quantum computers are commercially available. Almost all of the encryption that currently secures data center traffic, cloud communications, financial transactions, and government networks is based on mathematical problems that classical computers cannot solve in a reasonable time frame. RSA encryption, the backbone of internet security, relies on the fact that factoring large numbers into their prime components is computationally infeasible for classical machines. Elliptic curve cryptography, which secures everything from Bitcoin wallets to HTTPS connections, depends on a similar mathematical hardness assumption. A sufficiently powerful quantum computer running an algorithm called Shor's algorithm could theoretically break these encryption systems, not in years or decades, but in minutes. The threat is not hypothetical. It is a mathematical certainty once quantum hardware reaches a sufficient scale, and the timelines for that eventuality are getting shorter as hardware improves. This has given rise to a phenomenon called harvest now, decrypt later, where adversarial actors are already collecting encrypted data today with the intention of decrypting it years from now when they have access to a quantum computer powerful enough to do so. Every encrypted database, every secure communication, every piece of sensitive data currently protected by RSA or elliptic curve encryption is potentially vulnerable to this strategy. The post-quantum cryptography market, which covers the development and secure against quantum attacks, was valued at approximately $800 million in 2025 and is projected to reach nearly $18 billion by 2035. NIST, the American Standards Body, finalized 3 post-quantum cryptographic algorithms in August 2024, giving the industry a standardized set of quantum-resistant encryption tools to migrate toward. Every data center in the world that handles sensitive data has an obligation to understand when and how to complete that migration. The market numbers for quantum computing in data centers tell a story of exponential growth that is only just beginning. Quantum computing solutions generated less than $750 million in revenue in 2024. By 2035, JLL research projects that figure will reach $100 billion, a more than 130 times increase in just over a decade. Quantum computing hardware investments, currently around $2 billion annually, are projected to grow to $20 billion per year by 2030. IBM has described 2026 as a decisive year, with plans to deliver quantum systems capable of solving problems beyond the reach of classical supercomputers before the year is out. IBM's roadmap targets the first large-scale fault-tolerant quantum computer by 2029. Google has been demonstrating progress in error correction, one of the most fundamental barriers to scaling quantum computing to commercially useful sizes. Quira Computing updated its roadmap in 2026, planning to launch a fault-tolerant quantum system on Amazon Bracket by 2028, targeting 256 logical qubits from more than 10,000 physical qubits. Most industry roadmaps now converge on the 2028 to 2032 timeframe, as when the first TIA commercially meaningful fault-tolerant quantum systems will be deployed inside data centers at scale. This is not science fiction. These are engineering roadmaps from companies that have already demonstrated functional quantum hardware, backed by some of the largest capital commitments in the history of computing infrastructure. The hybrid model is how quantum computing will actually enter data centers in practice, and understanding this is critical to understanding what the transition will look like. No one is suggesting that quantum computers will replace classical computing infrastructure. The future of the data center is not quantum instead of classical. It is quantum alongside classical, with workloads being intelligently routed to whichever type of computer is best suited for each specific task. IBM is already running quantum processors next to classical supercomputers, using the classical hardware to handle the parts of a computation that benefit from conventional processing, while offloading the components that benefit from quantum speedup to the quantum processor. NVIDIA launched a family of open-source AI models specifically designed to manage the errors that plague quantum hardware, calling this the path to what it describes as quantum GPU supercomputing, a vision where quantum and GPU-based classical compute work together as a unified computational resource. JP Morgan Chase, AMD, and OQC are building a dedicated quantum AI data center in London, specifically designed to test hybrid quantum classical workflows under real financial services conditions. The architecture of the future data center is not a row of quantum machines replacing the rows of classical servers. It is a layered infrastructure where classical compute, AI accelerators, and quantum processors each handle the workloads they are designed for, connected by intelligent software that knows which layer to use for which problem. The data center real estate industry has a concept that Digital Realty's CEO described as a layer cake of demand, where each new wave of computing technology creates a new layer of requirements for specialized infrastructure. Classical servers were the first layer. Cloud computing was the second. AI GPU clusters are the third. Quantum computing is shaping up to be the fourth. Oxford Quantum Circuits has already moved quantum hardware into Equinix data centers in Tokyo and Manhattan. Digital Realty hosts quantum computing tenants alongside classical workloads. The infrastructure is being built. The standards are being written. The investment is flowing. The question is no longer whether quantum computing will reshape the data center industry. The question is how fast the transition will happen, which hardware architectures will win, and which organizations are preparing their infrastructure today versus discovering the urgency of that preparation only after the rest of the market has moved. What you are watching unfold across the global data center industry right now is exactly the same dynamic that preceded the cloud computing wave and then the AI wave. The technology is maturing faster than the general public realizes. The infrastructure build-out is already underway. The organizations that understand what is coming and begin adapting their facilities, their security frameworks, and their computational strategies now will be the ones who find themselves positioned at the front of the next era of computing. The ones who wait for the technology to be obviously mature and commercially dominant before paying attention will be the ones scrambling to catch up. The dilution refrigerators are humming, the qubits are cooling, the quantum data center revolution has already started. The workforce dimension of this transition deserves serious attention. Quantum computing requires a skill set that does not exist in abundance anywhere in the world right now. Quantum engineers who understand the intersection of quantum mechanics, cryogenic systems, microwave electronics, and quantum algorithm design are extraordinarily rare. The entire global quantum workforce is estimated in the tens of thousands, while demand is growing faster than universities can produce graduates. States and countries that recognize this are moving aggressively. Maryland launched a Capital of Quantum initiative in 2025 with $27.5 million in initial state investment alongside $200 million in matching funds. Singapore committed $300 million to a national quantum hub. The European Union funded quantum centers of excellence across multiple member states. For data center operators, this workforce scarcity is a real constraint on how fast quantum infrastructure can be deployed. Building a quantum-ready data center is not just about physical infrastructure. It is about having the people who can operate it, program it, and integrate it with classical systems in a way that delivers real business value. The pharmaceutical and healthcare use case illustrates the scope of what this technology could ultimately make possible. Simulating a molecule in enough detail to predict how a drug candidate will interact with a biological target is one of the most computationally intensive problems in science. Classical supercomputers can simulate small molecules, but run into fundamental limits as molecules grow larger. Quantum computers, because they operate on quantum mechanical principles themselves, are naturally suited to simulate quantum systems like molecules. Running a molecular simulation on a quantum computer is not an approximation of physics. It is physics. Drug discovery processes that currently take years of expensive trial and error could be dramatically compressed. The same applies to materials science, where quantum simulation could unlock new chemistries, superconducting materials, and industrial catalysts that classical computers cannot accurately model. A data center offering quantum simulation as a service becomes a scientific instrument that pharmaceutical companies, materials researchers, and climate scientists will pay significant premiums to access. JLL estimates quantum computing revenue from data center deployments could reach $100 billion by 2035, with a significant share coming from these simulation-heavy scientific workloads. The geopolitical dimension of quantum computing in data centers mirrors the semiconductor competition between the United States and China. Quantum computing is explicitly designated as a strategic technology by both governments. The Chinese government has invested over $15 billion in quantum research, including $10 billion in direct state funding for its national quantum laboratory. The United States responded with the National Quantum Initiative, quantum provisions in the CHIPS and Science Act, and export controls, targeting quantum computing components. This competition means that the location of quantum data centers and who has access to the hardware are not just business decisions. They are national security decisions. For enterprises choosing where to host quantum-sensitive workloads, understanding the geopolitical geography of quantum infrastructure will be as important as understanding the technical specs. A quantum data center handling sensitive cryptographic or molecular simulation, workloads cannot be selected on price and performance alone. It must be selected with full awareness of whose jurisdiction it operates under. This is the full picture of what quantum computing is doing to the future of data centers. It is not a simple upgrade story. It is a layered transformation that touches physical infrastructure, security architecture, workforce strategy, scientific capability, and geopolitical positioning simultaneously. The data center industry took roughly a decade to fully absorb the cloud computing wave and another decade to absorb the AI compute wave. The quantum wave is building now. The companies and organizations that begin asking the hard questions today, what does quantum-ready infrastructure actually require? How do we migrate our cryptographic systems before a quantum threat materializes? What hybrid classical quantum workflows are relevant to our workloads? Which hardware architectures are most likely to scale commercially? Will be the ones who look back on this moment as the point when they made the right call. The ones who are still asking those questions in 2030 will be the ones wishing they had started sooner. The quantum revolution in data centers is not coming. It is here.